my teammate Nicholas and I, Liza, would like to show you the game that we have digitalized. We've used the FPGA board simulator and the C programming language to build this game. The game that we've chosen to build is called the Towers of Hanoi. Well, if this doesn't ring a bell to you yet, let's check this video out first. Interestingly though, according to sources, this game was actually invented by a French mathematician in the 19th century. But instead of having 3 disks on Tower 1, there were actually 64 disks on Tower 1. And they hypothetically wanted to move these disks onto Tower 3, given that you cannot place a larger disk on top of a smaller one. So how long would it actually take to move them from Tower 1 to Tower 3? Well, let's just assume each step took 1 second. Even then, to move all 64 disks from Tower 1 to Tower 3 would take billions of years. That is more than the age of the universe that we know about today. That's crazy. So let's just look at this recursive problem and the rules of the game. Alright, so now let's take a look at the goal and the rules of the game. The goal of the game is to move the disks from Tower A to Tower C in such a way that the formation of the disks stay the same, such that the yellow is at the top, orange is in the middle, and the green is at the bottom. But there are 3 main rules. First of them is that we can only move 1 disk at a time. The second is that we can only move the upper disk at a tower. And the last being, we can never place a larger disk on top of a smaller one.
So our project was designed incorporating an FPGA board that contained a variety of input and output devices to get our game working. So what exactly is an FPGA? A field programmable gate array, which is what FPGA stands for, is basically a type of integrated circuit that anyone can configure to their desired specifications. In simpler terms, it's a device with an array of programmable connections of logic blocks. So there are many of these available, but for EC243, the specific board we use is called the DE1-SoC board to emulate the ARM Cortex A7 microprocessor. But due to the COVID-19 pandemic, we students haven't been able to access the physical labs that contain these boards. But fortunately, thanks to Dr. Henry Wong, he's a former student of our Professor Jonathan Rose. He made an online simulator called CPUlator where we programmed our Towers of Hanoi final project.
Let's take a look at the input and output devices we have implemented to make this game possible. To start off, we use the VGA pixel buffer to display our gameplay. We use switches to allow the user to select a certain mode of the game. For example, a certain level of the game, or actually unlock a certain feature, that is the autosolver. And we've used LEDs just to clarify that they have selected the respective switches. So let's take a look at this one. If the user clicks on 0, the respective LED shows up and we would be playing level 1. In level 2, we would have 4 disks, and in level 3, we would actually have 5 disks. And then we implemented the 7-segment display to display the minimum number of moves it would take to finish level 1 and the current number of moves the user is currently at. For example, for level 2, that would be a minimum number of moves of 15. And for level 3, that would be a minimum number of 31 moves. We've also, of course, implemented the keyboard to allow the users to play the game. Interestingly, we also had to implement a private timer for the autosolver, because if it was for the program would actually solve the game within milliseconds. But for the human eye to actually see each and every move, we had to use some sort of delay. And that was done by the private timer, we implemented a delay of 1.5 seconds. Last but not least, we implemented our character buffer, and that is, for example, on the right, that is to help our user if there was in fact an invalid move.
So here's how to play our game using CPUlator. So just begin. Here's our code in the background. Here's the VGA pixel buffer. And to our right, you can see the LEDs, switches, push buttons, and the PS2 keyboard or mouse input. So we programmed our game to play with 3 levels of difficulty. You can choose to play the game with 3, 4, or 5 disks. So let's begin. First, we must compile our code. So we hit compile and load. And it's compiling. And our code compiled successfully, as you can see on the bottom left. So next, we're gonna hit continue. And here's our home screen of the game. Towers of Hanoi by Nicholas Urlal and Liza Babaoglu. So let's begin. We're gonna select the mode. To keep things simple for our demonstration, we're gonna select 3 disks, and you can do this by selecting switch 0. But if you want to do switch, if you hit switch 1 or 2, you can do 4 or 5 disks. So yeah, let's start. And here's the game. Now, before we continue, take a look at hex 0, hex 1, hex 4, and hex 5. You can see it here. One says 07 and one says 00. So to the left, 07, this is the minimum number of moves it can take to complete the game. And the 00 represents the number of moves we have made. We haven't made any moves so far. So to begin playing the game, for the game to know what moves we're making, we can connect our keyboard by clicking into the PS2 keyboard input device here. Now we can either use the WASD keys or the arrow keys to move disks, like this. Now, if we were to make a mistake and make a wrong move, for example, placing a bigger disk onto a smaller disk, an invalid move message would be written into the character buffer and be displayed on the screen. So we can't make that move. And let's just continue playing, trying to solve the puzzle. So this is how you solve the puzzle. I did it in 8 moves, but I could have done 7 moves. So if at any point you want to restart the game, you can press the R key and go back to the home screen. Regardless of the number of moves you make, if you solve the puzzle, you get a win screen, as you can see here. So I'm going to click R to restart, and we're going to go back to the home screen. So we also built in a neat auto solver if you can't exactly solve the puzzle yourself. So the auto solver can do all 3 modes, the 3 disks, the 4 disks, or the 5 disks. So we're going to demonstrate the auto solver for 3 disks by clicking switch 7. Here it goes. And this is how you would solve the puzzle with 7 moves, which is the minimum number of moves. So next, we're going to talk about some of the fine details behind our code. So in our code, the primary data structure utilized was a linked list. Each tower is represented by a linked list. So for each tower, if the head node is null, it's an empty tower. And here's the linked list node. We also have another data structure that represents the arrow seen earlier in the game. We use this arrow to tell us important information such as which disk is suspended, where the arrow is currently located, and what's at the top of the tower that you're currently pointing at. Here's a look at that data structure for the arrow. So at the start of the game, the first tower is initialized with the number of disks chosen with the largest disk number at the beginning of the list. You can see here, earlier we get the number of disks and we initialize the first tower. You can see that with the helper function here. And another thing is, the only way to move a disk to another tower is if either the next tower is empty or if the last node on that tower, which would be at the top, is larger than what the arrow is currently holding. And for a win to be detected, the game is constantly checking in an infinite while loop to see if the third tower of this we started with is completed. You can see an infinite while loop here. And there's inside that infinite while loop, we're always checking to see if the game has been won. So the visualization of the gameplay was only possible due to an extensive amount of helper functions, as you can see here. In order for smooth transitions, by the way, instead of clearing every pixel on the screen, whenever a disk or the arrow is moved, we only draw on those pixels that are currently occupied. Another noteworthy detail is how we connected our code to the input and output devices. Using the FPGA manual, we made the connections by specifying the addresses of each I/O device. So take, for example, the delay effect we used for the autosolver. Each frame appears every 1.5 seconds exactly. We calibrated this using the ARMv7 private timer, as you can see here. And we put in brackets, we commented in the code that the 1.5 second delay is achieved because we knew the CPUlator model of the FPGA board runs at 200 megahertz. And using other appropriate settings and techniques, such as, for example, the polling of certain bits of the timer's registers, we were able to configure this I/O device and many others we used for our intended purposes.